Example 11.7. An iron bar length L1 0.1 meter, area A1 0.02 meter square, thermal conductivity K1 that is 79 watt per meter Kelvin, and a brass bar length L2 0.1 meter, cross sectional area A2 0.02 meter square, thermal conductivity K2 109 watt per meter Kelvin, are soldered end to end as shown in the figure. The free ends of the iron bar and brass bar are maintained at 373 Kelvin and 273 Kelvin respectively. Obtain expression for and hence compute the temperature of the junction of the two bars. 2. The equivalent thermal conductivity of the compound bar. And 3. The heat current through the compound bar. It implies that now in this question we have to derive the equation for the temperature at junction, and then using this given data we have to calculate that one. Then after we have to derive the equation for the equivalent thermal conductivity of this compound bar, and we have to calculate it. Then we have to derive the equation for heat current, and then we have to calculate it. Clear the question? Now lengths of both the rods, that is the same one, as well as their cross-sectional areas are same one. One end of the iron rod is at a temperature T1 equal to 373 Kelvin. Suppose the temperature at the junction of iron and brass, that is T0, and temperature of the other end of brass rod, that is T2 equal to 273 Kelvin. Length of both the rods, that is same one, so say it is L, that is 0.1 meter. Cross sectional areas of both the rod, that is same one, so say that is A equal to 0.02 meter square. Thermal conductivity for iron, that is 79 watt per meter Kelvin, and thermal conductivity for brass K2, that is 109 watt per meter Kelvin. That is given. Now see, heat will be transferred from left to right in this figure. So in steady state, we can say heat current through iron bar as well as through brass bar. That will be the same one. So first write down the equation for heat current. So heat current through iron bar, K1 A1 into T1 minus T0 upon L1. And the same heat current is flowing through the brass bar. So we can write that is equal to K2 A2 into T0 minus T2 upon L2. Now A1 A2, that is same one, so cancelled. L1 L2, that is also same one, so cancelled. So we can write K1 into T1 minus T0 equal to K2 into T0 minus T2. Simplify both the side. So K1 T1 minus K1 T0 equal to K2 T0 minus K2 T2. Now take this K1 T0 from left hand side to right side, and this K2 T2 from right side to left side. So we can write now K1 T1 plus K2 T2 equal to K1 T0 plus K2 T0. We want to find T0. Clear? Therefore, make T0 as a subject. So here on right hand side, take T0 common. So into bracket K1 plus K2, left side as it is. So finally we can write T0 that is equal to K1 T1 plus K2 T2 upon K1 plus K2. So now equation for the temperature at the junction is derived. Now substitute the values. K1 that is 79, T1 that is 373, K2 that is 109, T2 that is 273 upon K1 plus K2. So 79 plus 109. Solve this one, you will get the temperature at the junction. Clear, Aisudi? Now let's derive the equation for the equivalent thermal conductivity. See, for rod 1 we can write the heat current H that is equal to K1 A1 into T1 minus T0 upon L1. Now K1 A1 upon L1 into T1. Now replace this T0 by this derived equation. So T0 that is K1 T1 plus K2 T2 upon K1 plus K2. Now take K1 plus K2 as LCM. So K1 T1 plus K2 T1 minus K1 T1 minus K2 T2 upon K1 plus K2. So K1 T1 K1 T1 cancelled. So we can write H equal to K1 A1 upon L1 into bracket. Now in numerator take K2 common. So K2 into T1 minus T2 upon K1 plus K2. So we can write H equal to K1 K2 upon K1 plus K2 into A1 into T1 minus T2 upon L1. Okay. So T1 that is the temperature at one end of the iron rod and T2 that is the temperature at the other end of the brass rod. Okay. Now see H that is K1 K2 upon K1 plus K2. Now area of cross section for both one that is same one. So this A1 that is replaced by A into T1 minus T2 as it is upon length of both the rod that is same one. So L1 is replaced by L. Now suppose we think about the composite system. Then for composite system we can write the equation for the heat current. H dash equal to now equivalent thermal conductivity into cross sectional area throughout the system. It is A. So A. Now temperature difference between two ends of the system T1 minus T2 upon length of the system. So both the rods are with same length L and L. So total length of the composite system that is 2L. Heat current if you calculate by this one or by this one, heat current remains the same one. Okay. So we can say this H dash that is H itself. So now we can compare these two equations, these two. Okay. So K equivalent into A into T1 minus T2 upon 2L. That is equal to K1 K2 upon K1 plus K2 into A into T1 minus T2 by L. So A cancelled, T1 minus T2 cancelled, L cancelled. So K equivalent by 2 on left hand side equal to K1 K2 upon K1 plus K2. So K equivalent that is 2 K1 K2 upon K1 plus K2. So we can say this one is the equivalent thermal conductivity of the compound system. Now substitute the values. K1 79, K2 109 in this equation and solve it, you will get the answer. So equivalent thermal conductivity, for that the equation is derived as well as it is calculated. Clear to all of you up to this one? Now heat current. So for heat current you can take either of the three equations. One that you can write for steel rod, H equal to K1 A1 T1 minus T0 upon L1. Other equation you can write for brass rod, H equal to K2 A2 into T0 minus T2 upon L2. Or third equation you can write for the compound system, H equal to K equivalent into A into T1 minus T2 by 2L. Now use either of these three equations and substitute the values. Suppose we take this equation, then substitute this value of K equivalent, calculated one here. Area of cross section given to you. Temperature T1, temperature T2, both are given to you, and length L is also given to you. So substitute the values, you will get heat current. Clear to all of you?